I used to do graphing for, let's see, lab 1. Graphing techniques. I used to do a computer exercise where we gathered data and put it in the computer and had Excel draw the graph for us. But I realized that many students have never graphed by hand. So you don't know, you don't have a feel for what that data is actually doing and where you put it in the graph. So I found this one where you do it by hand. Once you've done it by hand, then you can use Excel or some other graphing program to help move things along. Once you realize what the numbers are for, where they go, and how to present them. So when we're looking at graphing techniques, we're graphing data. In other words, numbers that you obtain from an experiment. And for this particular one, this particular exercise, we're looking at pairs of numbers. So if you, and one of the examples in here is from Boyle's law, a gas law. So if you confine a gas and you put a certain amount of pressure on it, it will occupy a given volume. All right. So we're actually graphing pressure against volume. So each time you change the pressure, you get another volume. Right? So they come in pairs like that. All right. Now, in the sciences, we identify variables, things that can change. And then the question is, who changed them? Did the experimenter change them? In which case they're independent variables. Right? They're based upon whatever the experimenter does. So in this case, we're changing the pressure. This is the independent variable. And then this responds to it. This is the dependent variable. Okay, that's our definition. Whoever changes it, that's the independent variable. If the experimenter changes it, it's independent. So how do we put that on a graph? Well, we're going to use the Cartesian system. That is simply XY. So the complete Cartesian, if you had this in math class, probably didn't. Everybody had the Cartesian coordinate system? No? Okay. Well, this is new for some of you then. Okay. That's the complete Cartesian system. This is called the abscissa. Let me spell it right. Or the x-axis. And this is the y-axis, or the ordinate. Okay. As far as our data set goes, we put the independent variable on the x-axis. We find it, whatever that number is, we find it here. So in this case, it'd be pressure. And then the dependent variable is when we move out to here, then we go up, however many units it takes. And that place has the x. Well, it would be xy, or it would be P1, B1. Those two numbers tell you that point. Okay. And we do that for all of our data set. By the way, this is called the origin. And what's the coordinate for the origin? 0, 0. It's always that. Anything to the right here is positive. Anything to the left is negative. Anything above is positive. Anything below is negative. So over here, you're going to have positive values. And this is where we spend most of our time. or most of our data is going to be in positive. Occasionally, you'll go over here, maybe into the negative positive, and sometimes below. But most often you'll be in this quadrant. There are 4 quadrants here. I think one of your examples takes you into the negative. All right. Okay. So another one of the other, actually, this is pressure volume is the second one exercise that you do. The first exercise has temperature volume. Temperature volume, that's Charles' law. So if we plot that data and we take each data point and we say at this temperature you have that volume. At this temperature you have that volume. So you know as you increase the temperature, if the pressure is constant, you increase the temperature, the volume increases, right? So we plot those out and they should give us a straight line if we connect all those dots. Okay. And these are the measurements that were actually made. Right. So we know those are, well, within certain error. Those are values that we can depend on. But within these, we can also use that best fit curve to say, all right, what temperature would it take for the volume to be here? So we go across, and we come down. So it'd be that temperature. I mean, we didn't measure that one, but based on our data, that's the best guess is the volume here would be related to the temperature there. That's called interpolation because we're inside the boundaries of the measurements we've made. But occasionally we want to know what if you go outside those boundaries, right? Right. If you ask questions about these here, that's extrapolation. You're outside the measured boundaries. And you have to be really careful when you extrapolate because you don't know what that curve, you're pretty sure the curve is straight in here. But once you get past that last mark, you don't know where it's going. It might go like that, it might go like this, over here, over there. So extrapolation is more hazardous than interpolation. Now I mentioned best fit curve. How do you determine a best fit curve? Well, let's say you have measurement here, 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 here. Best fit curve is going to minimize the distance from the line that you draw and the points that are available. So you wouldn't draw it over here. That's too much. You wouldn't draw it over here. You draw it kind of in the middle. Yeah. And that minimizes the deviation from the curve. That's a best fit curve. Now, this is a straight line best fit. You can have curves that are best fit. In fact, when you plot pressure against volume on this system, it's going to be like that. Right? It's going to give you a hyperbola. Remember what a hyperbola is in math class? You don't have to remember the formula, just characteristic. A hyperbola is like this. It exists in one quadrant. It doesn't have to, but it usually does. But in this case, this one, no matter how far you extend it that way or how far you extend that way, it never touches the axis. Goes on for infinity. And just get closer and closer and closer, but never touches it. That's a hyperbola. Okay, let's see. All right. Okay, one other thing. The relationship between temperature and volume here is as the temperature increases, the volume increases, right? And this is a positive slope. What's the slope of a line? Rise over run, right? So if you can calculate here to here, This change in volume is the rise, and this change in temperature is the run. So this one divided by that one is the slope of the line. And this is going to be a positive move. This is going to be a positive move. So the ratio is positive. So a positive slope indicates a direct proportion. As one variable increases, the other one increases. And if it goes the other direction, you're going to do the calculation and find out that the slope is negative. If it slopes that way, it's negative, and that indicates an inverse proportion between the two variables. Now, what if we have, if we draw that curve like this again, what kind of relationship is that? Well, with one tweak, it's a negative relationship. It's a negative slope, which indicates an inverse proportion. But it's a different slope every point on the line. When we talk about curves and slopes, we have to talk about instantaneous slopes. So here, the slope would be the tangent to that line. That's negative. Tangent to the line here will be negative, negative there, negative there. So they're always negative, but they're different slopes because it changes. Okay. All right. Let's see. Now, when we're drawing the data, when we're actually putting it on paper, and you've got some graph paper there at the back of that method, but it may not be enough. So I've got some extra graph paper here somewhere. Got to just find it. That's gonna be it. They'll look straight at it. Look right through it. Look at the labels. I give you guys a safety contract. And this is in the other class. That's the Zoe's that we. Zoe's from 102, 104 class. She decided we're going to compete with you guys. And I gave you guys a safety contract. It's the same contract, and if you hand it back to me already, then you're covered. Okay, so just when you get a chance, hand that to me. Find this. Here. There it is. So if you need extra graph paper, then I got some here. Only I forgot to tell it not to staple it together, so we'll have to rip it apart. Okay, here we go. So when you're taking that graph paper and you're gonna create, it's just a blank sheet of graph paper. If you're going to create your graph, you got to say, all right, where do the axes go? Right, so you need to make a decision. Where's the best place to put your axes? And guiding principle is you want to maximize the use of the available space. You want to spread everything out as far as possible so that it's easier to read. Right? If you have everything crunched together in a little space, it's difficult to do what ifs, interpolate or extrapolate. Read your graph. You want it as big as possible. So the first thing you have to decide is what are the ranges That's not gonna work. What are the ranges of values? For your X and Y axes. You know, how far do they go? Like from 0 to 100 or 0 to 50 or 0 to 1,000? How big are they? And then you decide which one needs the most space. Right? The one that needs the most space on this sheet of paper, it can either go this way or that way, portrait or landscape. You know, if the x-axis needs more space, then you do landscape because it would go farther across the bottom, shorter across the top. If the y-axis, the dependent variable needs more space, then you do it this way. So that's based upon the ranges of your values. And then you decide from there, portrait or landscape. Okay. Then, once you've decided that, then you have to say, divide the axis, divide units on your axes. So you take your paper, right, and it's got the hash marks here and here. That was wearing it up too. I got a dark brown, maybe that'll work. And you decide where do you want to actually draw your 0 axis, like here, here. So this would be your origin at 0, 0. If some of your data points are negative, then you would either extend it this way or this way to accommodate them. And that means you have to shift it over to take those into account. And you draw your 0, 0 axis here, wherever it happens to be. Right. Because your abscissa and your ordinate have to be originate from origin. That's redundant. Okay, then you say, okay, with the ranges of values, I'm going from such and such to out here. Then you have to say, how far can I go and use these regular marks so that they're easy to read. For instance, with that graph paper, you've got heavy lines and light lines. Right? The heavy lines, between the heavy lines, there are 5 divisions. Right? That's a little awkward to use. If you can get it, make one of your units between 2 lines. Then you have 10 divisions between them. And that's like tenths. It's easier to do decimals than it is fractions anyway. Right? So you would take maybe 2 of these, and this would be maybe position 1, and this would be 2. That way you could have 10 divisions for tenths there, just as an example. And you do the same thing for the y-axis. And you want your largest number, your highest number, to be as far out here as possible. So if you count them off and you say, okay, if I count them off in regular units for my ranges, and my highest range is going to be out here, you're going to have to shrink it back by a factor maybe of 2, come back to here. So you can't use the whole thing. But it's better than dropping one of your numbers off the edge of the paper. And once you've decided that, then you draw in your major tick marks, they call them, and label them. Label both of them. And then in this case, we would say this is P and the units of measure, atmospheres. Okay. And this would be volume, and it's probably in milliliters. Okay. So you have the tick marks marked off and labeled. You have the axis labeled and units given for both of them. And then you need a title. What is this? Relationship of gas pressure to volume. Needs a title. And then you put your points in there, right? And then you draw your best fit curve. and your graph is done. The rule that you live by with drawing graphs is every graph must stand alone. In other words, if you extract it from your work and somebody looks at it, they can gain some information from it. They know what it's about. They know what the independent and the dependent variables are, what their units are. They see the best fit curve, and they can interpolate or extrapolate at will and get numbers off of it. Graphing data is a visual representation of the results of your experiment. Some experiments produce thousands of pairs of numbers. And graphing is very often the only way that you can make sense of all those numbers. I mean, we have statistical programs that will spit out values for you and help you along the way. But if you want to study your data and see what it's doing and see if it makes any sense to you, then graphing is the best way to do it. And there are hundreds of different ways to do graphs. So we're just scratching the surface here. Right? You can do three-dimensional graphs, multivariate graphs. You can have several axes. Lots of times you'll have the same x-axis and you'll have one axis here for one set of numbers, and then you'll have another axis over here for a different set based on the same independent variable. And that means you'll have two sets of data and you have to designate the differences there, like squares and triangles and circles, and then draw best fit curve for the two different ones. That way you can get a lot of information on a single graph. So the sky's the limit. What's the best way to represent your data so that you can make your argument stick? Right? If you put this in a publication, you want it to support your argument. You're saying you think this is what happened in your experiment, and this is why. And supports your evidence. And you can put other things in here, like statistical values. Like if it's a straight line, you can put the y equals mx plus b formula for the straight line here. And then you can also put an r squared value, which says how close does that line you drew fit to the data? The closer it is to 1, the better. It'd be a fraction. I've seen 0.87 and they're making claims with that, but 0.9 or better is better. And that's an argument for anybody who takes statistics. All right, you get to hammer on that a little bit. Okay, so let's see. Ranges, portrait landscape, divide units on axes. And then as a corollary to this one, you want subunits. And I mentioned that when we talked about it. The subunits between the lines, you want to identify what the subunits are, and the best way is to do tenths if you can get them, like 10 units between the marks. If you can't, then you can shrink it down to maybe 0.2 per mark. It's more difficult to read it, but you may not have the choice. Let's see, don't leave anything out. Cover all the bases. Graphs have to stand alone. We calculated the slope of the line. Right? That's in here also. Now, the nice thing about drawing a best fit curve, if the best fit curve is a straight line, then if you have a straight line in here and you have a data point here that falls right on the line and data point here that falls right on the line, but the rest of them are kind of scattered, that's good, because now you can use this one and this one to give you your rise and run, right? So there's your delta y and there's your delta x right there. And you've got numbers that you can use to do that. If then none of them fall on the line, then you have to draw the best fit curve, and then you have to read an interpolated position for each one, and then determine the slope, rise over run. Change in y, so you can go from here, subtract that from here, You go from here, subtract that from here, and that would be your delta, your change. Okay. All right. Pay attention to the figures in here. They will be helpful. Figure number. See if I was saying this right. Yeah, figure number 2 is temperature versus volume. Okay. Figure number 3 is pressure versus volume. Let's see. Pressure versus volume. Oh, about the entire exercise, there should be. This is an informal lab, so you just complete it. And that's why there are points listed on the page. So we're not going to do a rubric for this one. This is informal, not a formal lab. The only thing you have to do that's not here is in the answer blanks is draw the graphs. But it should be subdivided into a required section and a bonus section. Yeah, bonus section. Now these pages are not numbered right, but it's 29 at the top. So everything after this is bonus. Okay. And some of those bonus graphs are kind of squirrely. One of them, you draw added base, sodium hydroxide. And then the response is pH. And I know we have to define pH, but that's a measure of acidity. So when you draw it, you're going to get something like this, a sigmoid curve. That's your best fit curve for the data. And then there's another one in there that draws temperature and time, I think. It's like time in seconds and temperature in degrees C. And it'll go up like this, and then it's a broken curve. You got data points in here, and then all of a sudden it goes like that. So if it asks you a difference between something and something, what you may have to do is you may have to extrapolate until you reach a point where it will intersect some part of this curve to know the difference there. But that's a bonus, so you don't have to tackle it unless you want to. Let's see, let me get back to required section. Okay, so the first pages of the required section are pretty much definitions, and even on the second page. So when you get to the third page, number 8, that's where you have your data set of temperature and volume, and you decide, all right, which one is the dependent variable, which one's the independent variable. The independent variable is the one that the researcher controls, in this case temperature. So temperature will go on the x-axis, y-axis would be the volume. Okay, and then you draw it out, and you use your graph to answer questions 4, 5, and 6, and 7. Okay. So in this case, when you draw that line on your graph and you find the slope of it, right? So you get the slope out of this rise over run from your data set. Then you're using this model as your straight line. So there's your slope, goes right in here, right? How do you find the y-intercept? Where does this thing intersect the y-axis? Well, once you know the slope, all you have to do is take one of your numbers from your data set, plug it in here, the x and y values, right? For any number on that line, preferably one that actually intersects the line. And then you got your slope, and you've got an equation in one unknown. You solve for the slope, the y-intercept. And then you can write it out as, let's see, if it's temperature and volume, this would be volume. So V equals whatever you determine to be the slope times temperature. These are variables. These are variables. These are numbers plus whatever B is. So these numbers will be determined, and then you'll have those. Or you could write it out y equals number x plus number. That's okay. All right. When it asks for an equation, that's what it's asking for. And then we get to pressure volume. Draw that one out. That's Boyle's law. We're going to get to gas laws later, but this is an exercise in what do you do with the data. Because that's going to be a formal report when we get to Boyle's law. And by then you'll have had this experience, and you'll be able to produce some pretty graphs. If anybody proficient in Excel, right? Yeah, I've done it before. So you've done some graphing with Excel? Yeah. Okay. That would be useful when you do your final report, because it look better. Okay, and then after that, let's see, temperature, volume, pressure, volume. After that is bonus. So there are two other graphs in the bonus section that you could draw if you want. But you need actually you need three graphs. The temperature volume is one of them. That's a single exercise with the data set. But with Boyle's law, you got pressure and volume, right? The independent, dependent, but that gives you a curve. And scientists don't like curves if they can get away from it. So what we're going to do is transform the data to give you a straight line. Okay, and here's the way you do it and why you do it. Boyle's law says pressure times volume equals a constant value. That means as pressure goes up, volume goes down. I pointed the wrong one, didn't I? As pressure goes up, volume goes down. But this, if you plot pressure against volume, multiply them together, you always get the same number. And that gives you the hyperbola. But can we transform this into some form that will give us a straight line? Well, as a matter of fact, we could. We can use the rules of algebra and say, okay, we're going to divide both sides by volume, right? That's kosher. That means this volume cancels. And this volume now is where our equation is like this, K over V. Well, I want to separate that out. Can I do that? K times 1 over V, correct? That's legal. Okay. Notice the form. Y equals mx plus B. So what's B? Well, in this case, B is 0, right through the origin. So if you take the volume and just divide, take the inverse of the volume, you get another data set, pressure against volume. Now you're going to put pressure on the x-axis and 1 over V on the y-axis. Now when you plot it, this is going to be a positive number, and you get a straight line. And the slope of the straight line is that, if I can write, is that K value. And the line is going to go through the origin. So when you draw the graph, what changes? Does the pressure change? No, it's the same pressure values. So it's going to be pressure in atmospheres. What about this one? This was probably milliliters. So what's the value here? What's the unit of measure for 1/V? Remember, when you do anything to a number, you do the same thing to a unit. So when you take the inverse of the number volume, you take the inverse of the unit. So the unit of measure here is mLs to the -1. Okay, and that's what you plot for the second graph using that transformation. You have to do it yourself. You have to go through and take the inverse of every volume and then plot the pressure against the 1/V. Most calculators have the 1/X key. But if it doesn't, just say 1 divided by the number. Works the same. Takes a little more effort, but it still gets you the answer. Okay.